All right, so what is meant by a balanced force? So here you have this example right here. You see, you have this book sitting on a table, right? So the book, The Game of Thrones, is sitting on this table right here. And so you see there are balanced forces. And like it says down here, if the forces on an object are equal and opposite, they are said to be balanced, right? So the two forces we're talking about right here in this case is the table, the force of the table pushing up on the book, and then gravity, which pushes down on the book. And if y'all don't know, gravity is this force on Earth that keeps things from floating off into space, right? It is what keeps us grounded to the floor, and it is what has apples falling to the ground when they fall off their tree and not just floating off into the sky, right? So this is what causes us to weigh what we do here on Earth because gravity is pushing us down to a certain extent. Right. So here are the two forces again. The gravity is pushing down on that Game of Thrones book, and you see that right there in the red. Right. And then you see in the blue, the table is pushing up on the book. And so the acceleration is 0 meters per second, which means the book isn't moving it, right? It's not going anywhere because the table is pushing it up and gravity is holding it down, right? So the objects here experience no change in motion because, again, they are balanced, right? The gravity pushing down on the book, the table pushing up on the book, and that is balanced, right? But what happens if we were to move, or actually, let me phrase it this way. What would happen if you remove the table? Right? If you remove the table, the book would fall to the floor. Gravity would push it down, and there would be some acceleration, right? As fast as it is moving to the ground, that would be the acceleration, right? But think about it this way, too. What happens if the book was sitting on a table and you just removed all the gravity in the room? If you removed all the gravity in the room, then it would no longer be a balanced force, and the book would float up into the atmosphere. Right. So that is what this is saying right here is that these forces are balanced. So the book isn't going anywhere, right? It's staying put on that table. But what about here? You see, now we're talking about unbalanced forces, right? Before the book here was a balanced force and the book just sat there. But now we're talking about an unbalanced force, and that means net force, right? Net means overall. So overall, there's going to be some force. And in this case, you can see, especially when you look at the arrows right here, look at the arrow for the rocket, the force from the rockets, which is where the fire shoots out of, versus the force from the gravity, right? So when the rocket is first standing there, gravity is holding it down, right? Gravity keeps it down on the ground, but this rocket needs to blast off with so much force that it's going to break from the force of gravity and go up into the sky, right? And eventually into space. Right. So what it says down here, if they're not equal and opposite, then the forces are unbalanced and the motion of the object changes. Right. So again, gravity is holding it down. That's what's keeping it down. And it's being held up on that little launch pad, right? But the launch pad is holding it up and gravity is holding it down. But once those rockets explode, there is enough force there to break gravity's force and break through that and go up into the sky. And that's what you're seeing right here during this blast off. Right, here's some more examples from real life. A soccer ball sitting at rest, it's going to take an unbalanced force of a kick to change its motion. Otherwise, it'll just sit there. Right, another force, though, is like the wind, right? If it's windy outside and a soccer ball sitting out on the grass, it's going to start rolling due to the force of the wind. If two teams are playing tug of war, they're both exerting equal force on the rope in opposite directions, right? And if they're the same strength, it's going to be a balanced force, and it's not going to result in any change of motion. Kind of what you see right here. And so his first law, Newton's first law, is also called the law of inertia. And inertia is just this, the tendency of an object to resist changes in its state of motion. What that basically means is that an object in motion will stay in motion and an object at rest will stay at rest, right? Unless some unbalanced force acts on that. So the first law states that all objects have inertia, right? The more mass an object has, the more inertia it has, and the harder it is to change its motion. That's why you need to buckle up when you're driving, right? Because if you don't wear that seatbelt, you're driving 80 miles an hour, your car hits some object, you're still going to be going 80 miles an hour. And if you don't have that seatbelt, you'll fly out the windshield because of inertia, right? And here you see that hamster wheel too, right? It's running, and then it stops. That inertia keeps the wheel spinning and it causes the hamster to spin in its wheel. Right, here's some more examples from real life. Right, so we have a locomotive, right? A powerful locomotive begins to pull a long line of boxcars that were sitting at rest. right? But because the boxcars are so massive, they have a great deal of inertia. So it takes a large force to change their motion, right? From not moving at all, it's going to take a lot of force to get them to start moving a little bit. But once they actually pick up some speed and they pick up momentum, they're going to be a lot harder to stop. And once they are moving, it takes a large force to stop them. Right. And there's this movie called Unstoppable with Denzel Washington and Chris Pine. And this is basically what the movie is they pick up a whole bunch of more than they probably should be carrying boxcars. And someone ends up getting on the train, the locomotive, and they step out for a second, but without actually stopping the train. They were supposed to just hop back in. It goes out of control. It takes off without a driver or a conductor in the locomotive. It picks up so much speed that in one part of the movie they mentioned that if this train were about to hit something, it would be like a missile going off because of how much speed it has and how much weight it's carrying, and then the material that it was carrying too. Right. So if you got in the way of a locomotive like that, there would not be much left of you, right? You'd probably be pulverized. But if you're talking about on your way to school, a bug flies into your windshield. And since the bug is so small, it has very little inertia and exerts a very small force on your car, right? So you're not going to feel that. You're not going to get pulverized by that. But that bug was definitely going to get pulverized by your windshield, right? Because it's size, right? Size has a lot to do with inertia. You think about an elephant and a squirrel. Right? If you think about something startling them, the elephant is going to take a lot longer to get up and take off running. But the squirrel it'll just happen like that, right? In a snap. But think about once they get going, right? You put your hand out to try to stop the squirrel and it'll hit your hand and just bounce right off. You try to do that with the elephant and you're going to get run over, right? So, yeah, it has a lot to do with size. Football players too, right? Once they get that momentum going, that force will actually do a lot of damage if it hits you. Here you have a few other examples, right? And just know why they don't stay in motion. So things don't always keep moving forever because there's almost always an unbalanced force acting on them, especially here on Earth, right? Look at this little girl in the GIF right here to the right. She's trying to slide on a slip and slide, but there's no water on there, right? Whoever's filming her is pretty mean for doing that. But this is just showing that she stops. She does not slide because of something called friction. Right? The friction of her hitting that slip and slide is very strong, and that's why she doesn't go anywhere. If there had been water on there, though, that would kind of remove some of that friction, and she would be able to slide on that. Right? If you ever lived up north and just went like on slippery sidewalk, icy sidewalk, you'd go slipping on that because the ice creates very little friction. Right? So if you roll a ball down a carpet and you roll the ball down a sheet of ice, it's going to go a lot further on that sheet of ice because there's not as much friction as there is on that carpet. If you've ever run and then like accidentally slid on carpet, you know that it burns you. You get rug burn because of that friction of the carpet. If you hit a ball upwards, it's eventually going to slow down and fall down to earth because of gravity, right? If you were in outer space and you threw a ball, it would just keep going and going and going, and it would never stop unless it hit a planet or a star or got sucked in by the gravity of a planet or a star. Otherwise, though, it would just keep going and going and going. So when you talk about his first law, an object in motion will stay in motion, that's not talking about here on Earth because that doesn't happen, right? You throw a ball here on Earth, it's not just going to keep going and going and going. Eventually, it's going to stop because of gravity, because of wind, because of different types of friction. In space, though, that ball would just keep going and going and going and never stop. Right? So a little bit more about friction. You may be familiar with some of these types of friction. You have motion. It's like in an airplane, right? An airplane has to actually try to defeat that friction by how it's designed. And that's why planes are designed the way they are to cut through the friction of the air. And then you have friction in tires. This is very important. This is why you don't want to have bald tires or tires that are all worn out, because if you hit a patch of water, it's going to just slide on that patch of water, right? Newer tires will have those grooves in them that lets the water kind of cut through. So it creates a little bit more friction. Without that, you would just slide on the puddle of water. And this has happened to me before while driving. Motion of friction, you have different types, right? And it's just a catch-all term that collectively refers to all the forces which act to reduce motion, right? Basically, it's the things here on Earth that slow objects down and eventually stop them. And like it says on the bottom, right, transforms the energy of motion into thermal energy. And this makes sense. Thermal energy means heat, right? So again, if you slide on carpet, you are going to get that rug burn and it's going to feel hot, and it's because of that thermal energy. Right, so in outer space, away from gravity and any sources of friction, this is what I was saying. A rocket ship launched with a certain speed will just keep going and going